Basic definitions. So throughout this course, square brackets n is going to denote the first n positive integers. And the power set of a set x, so x is a set, the power set is going to be defined to be, so the notation I'll use is 2 to the x, for reasons that, well, might become clear later. So the power set, some of you may know, is the collection of all a, where a is a subset of x. And for example, if you look in the background of my video, you can see, so that's one of the definitions that you'll be able to see. So for example, what is the power set of square brackets 3? Well, okay, does anyone have a, does anyone have a, what's an example of an element of this power set? That's the smallest one. Go with that. So the empty set is a subset of 1, 2, 3, right? Then we got the set containing 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. So in particular, there's 8 elements, right? So that's kind of part of the reason for this notation. 2 to the size of the power set of 1, 2, 3 is 2 to the 3. And also there's going to be similar notation coming, which, yeah, is related to that. Okay. So the general question in the first 2 chapters of the notes, and those are the chapters on extremal set theory, is basically what is the maximum or minimum, maybe just maximum. So what's the max size of a collection of sets? So it's a collection F, which is contained in the power set of the numbers 1 up to n, which has a certain property. So out of all of the subsets of the power set, we want to find the biggest one subject to some kind of constraint. Okay, so this lecture is going to be about antichains. So an antichain is a collection of sets, so a subset of 2 to the square brackets n, such that there does not exist a and b and curly a, maybe I should make it more curly, such that a, so I'm going to use this, this is the notation I'm going to say is a subset, and I'm going to cross out the equal sign. So I mean, this means that a is a strict subset. So if I wanted to kind of expand this a bit, what I mean by this is a is a subset of b and not equal to b. Okay, because obviously if I take the same set twice, then it's a subset of itself, but that's not terribly interesting. Any questions about this definition? Is this clear? Okay, so we're taking subsets of 1 up to n. We want to take as many sets as possible, but the rule is you can't have one that's nested inside of another. Okay. Curly A is a collection of sets. Yeah, so I've written it, as curly A is a subset of the power set, but that means that, remember, the power set of, yeah, the notation here is a bit, you have to think about it. It takes a little bit of time to be familiar with it, but yeah, this is the collection of all subsets of 1 up to n. Curly A is a subset of that, so the elements of curly A are sets. So, I mean, the basic picture here is just, you've got some points and you've got some various sets, and let's say n is 8, whatever this looks like 8. And what you're not, so you can take a bunch of sets, and the rule is you can't have one contained in the other. So how many can you, so some examples, is this an antichain? So the first collection. Guesses, any thoughts? Would you say that's an antichain?
No, because the second one is a final one.
Right. That's the problem. 3, 4 is contained in 1, 3, 4. So that's not an antichain. But if I look at this one, 5, 1, 2, 1, 3, 4, 6, 2, 3, that looks good. Obviously, if I give you 2 examples, right, one's gonna work and one's not, right? Is how it works. Anyway, this one is an antichain. If you check all the pairs, you can see that none is contained in the other. Okay, so another definition. So if I have a set X, I'm going to define X choose K to be the set of all A such that A is a subset of X and the size of A is K. I guess I should say for a set X, a non-negative integer. All the subsets that have size K. Okay, observation. N choose, or square brackets N choose K is an antichain, right? Because if I take two different sets of size K, definitely can't have one sitting inside of the other, right? Because if one has size K and it's sitting inside of another one, the other one has to be at least K plus 1. So it doesn't, you can't have these things being nested. So therefore, for every K, there exists an antichain of size, oh, yeah, of course, so so how big is this thing? So the number of subsets of size K is actually N choose K. So the cardinality of this thing is N choose K. So for every K, you get an antichain of size N choose K. And what's the biggest that you can do in this, like if you're doing it this way? What I mean is, what is the maximum, which K maximizes N choose K? Right, so we have an answer in the chat. Indeed, yeah. So there's a slight issue that not all integers are even, which is annoying. Some of them are odd. But that just means you have to take a floor or a ceiling, it doesn't matter. So therefore we found an example of a big antichain in some sense. So we found an antichain of size N choose N over 2. This is just, so far this is just an example. So we haven't really solved the question that I was asking about what is the biggest antichain. So this is the only, this is just the biggest antichain you can make in this particular way. Any questions right now? Okay. So what I'm hoping to get through today is a proof of Sperner's theorem, which says that the largest cardinality of an antichain in the power set of the numbers 1 up to n has, so the largest cardinality is actually N choose N over 2, where whenever I say N over 2, I mean the floor or the ceiling. So actually, this thing where we took all the sets to be the same size is optimal. And this isn't trivial, right, this Sperner's theorem, because, of course, there's no obvious reason why this should be the case, right? In theory, you could take sets of all different sizes, and maybe that would do better. But it turns out, actually, the best thing to do is to take the sets to be the same size. So we're going to see two different proofs, one today and one on Thursday. This course is on Thursdays, right? Yeah. One today and one on Thursday, not on Wednesday. Today we're going to prove it using so-called symmetric chain decompositions. Okay. So the rest of the lecture now is focused on trying to prove Sperner's theorem. Okay. I need a definition. So a chain is a collection. A chain is basically the opposite of an antichain. So it's a collection, let's say C, in the power set of 1 up to n, such that either A is a subset of B or B is a subset of A for all A, B in C. So you should think of this as being the total opposite of an antichain. In an antichain, these things weren't allowed, but here every pair has that structure. So is this a chain? The first one this time, I guess, is yes. So to check something as a chain, it's kind of easier than an antichain, right? You just start with the smallest sets, right? The smallest set has to be contained in the second smallest set, which has to be contained in the third smallest set is over here, 1, 3. So empty set is contained in 1, 1 is contained in 1, 3, 1, 3 is contained in 1, 2, 3, and then therefore you have, it's a chain by transitivity of the subset relation. 2, 2, 3, 2, 4, 5, because of these guys. 2, 3 is not contained in 2, 4, 5. Obviously 2, 4, 5 is not contained in 2, 3 because it's bigger than it. Right, so you should think of chains as being the opposite of an antichain. I mean, if you've seen graph theory before, then this is kind of like, I mean, it's sort of like how an independent set in a graph is kind of the opposite of a clique, right? In an independent set, you have no relationship between any of the points, vertices. That's kind of like an antichain. You have no relationship between the A's and the B's, whereas a chain is kind of like a clique or a complete graph, right? You have interaction between all pairs in the set. Not sure if that helped at all, but here's a simple observation, but a very useful observation. So we're going to use this a few different ways, I think. So if I've got A and C, where C is a chain and A is an antichain, well, how big can this be, the intersection between them? So I want to say it's at most something. Any guesses? Thoughts? Oh, I think I missed some. Right, so I think the first question's been answered by somebody else. By the way, I totally encourage that. It's great if you can answer each other's questions. Right, and someone's also given me an answer here, and that's the correct answer. So if you have an antichain and a chain, they can only contain at most one common element. This is, I mean, if you think about the graphs and or the cliques and the independent sets, that's kind of clear, right? If you have a complete graph and an independent set, they could share one vertex, but they can't share more. So that analogy kind of works here as well. So kind of a proof, you know, suppose, so I'll do this quick. If A, B are in C, well, let's say that they're actually in this intersection, so, and they're not the same, then, well, you know that A is a subset of B, or B is a subset of A, because they're in C, but then this contradicts. Okay, we've done our first proof. Rather easy one. Okay, but weirdly enough, this is going to be quite useful. Okay, this is a kind of technical definition here. So a chain is symmetric if there exists an integer k such that k is somewhere between 0 and over 2, and C consists of a set, I'll say consists of sets of size k, k plus 1, k plus 2, ... up to n minus k. Maybe a picture. I'm not sure if this picture is going to be used. Let's try. This is my power set. This is the level. So suppose I've kind of organized my sets from smallest down here, the empty set, to the biggest up here. It's the whole set. And this is the sets of size n over 2. Let's say I'll omit the floor for now. So what a symmetric chain looks like is that it contains a set of size k for some k, and then it contains a set of, you know, one bigger all the way up. Well, let's say we started a bit lower. I'm not sure if this is terribly useful, but so you've got a set of size k down here, which is contained in a set of size k plus 1, which is contained in a set of size k plus 2, all the way up every level up to n minus k. And by the way, this makes sense because k is at most n over 2, so n minus k is at least as big as k. So it's just a special type of chain. Any questions about that? Okay, so is this a symmetric chain in 2, 2, 2, 3, 2, 3, 5, 2, 3, 4, 5, that's a chain. Is it a symmetric chain in power set of 1 up to 5? I think the answer is yes. But note that being symmetric depends on n, right? It depends on the number 5 here. So I would say yes here in 2 to the 5 because the smallest set, so you've got k equals 1, right? The smallest set has size 1, and the biggest set has size 4, which is indeed 5 minus 1. But this thing is also a chain in the power set of 1 up to 6 or 1 up to 7, but it's not considered a symmetric chain in that kind of universe. Is that clear? Okay, I've got only 8. Yeah, if a chain literally has no, actually let's go with no. the empty chain is not a symmetric chain. There has to exist some k, such that has k plus 1. I'm not sure I'm going to finish this in this lecture, but that's okay. We'll start with the proof. We'll continue next lecture. Okay, so a symmetric chain decomposition is a partitioning or partition of power set of n into symmetric chains. Okay, and so the lemma, which basically is going to almost completely prove Sperner's theorem, is that for every n, at least one, power set of 1 up to n has a symmetric chain decomposition. So I'm going to focus on proving this, and then if I get through that proof, then we'll use that to prove Sperner's theorem. Okay. Any questions though before I move on? So I've just restated the lemma here. Proof is by induction. Well, as usual, the base case is not too bad. So we're doing induction on n. In the case n equals 1, what is the power set of the set containing 1? It's just the empty set and the set containing 1. So this just is a symmetric chain just by itself, because it starts with a set of size k equals 0 and ends with a set of size n minus k, which is 1 minus 0 equals 1. Okay, that was easy. Now for the general case, n is at least 2. So we're going to use induction. So we can find a symmetric chain of the power set of numbers 1 up to n minus 1. And we want to sort of transform this into a symmetric chain decomposition of the power set of 1 up to n. So, okay. So this notation, so curly C 1 up to curly C capital N, those are so curly Ci is a symmetric chain in the power set of 1 up to n minus 1, and these symmetric chains partition that power set. So just a bit of notation. For m between 1 and n, I can let km be the minimum size of a set which is in the mth chain. And then I can, so all of this just now is just setting up the notation. Write C, the mth chain, as xm km, m km plus 1. I apologize for the notation. I thought about this notation a lot, but could not come up with anything better. Up to xm n minus 1 minus km, where the size of xmi is I, so for all. This km just determines what's the size of the smallest set, which, because these are symmetric chains, that determines the size of all of the sets. And notice that this, remember, we're dealing with the power set of 1 up to n minus 1. So the biggest set in Cm will have size n minus 1 minus km, rather than n minus k, right? Because we're in a smaller dimension. Okay. So now I'm going to define, for each m, I'm going to define Cm prime to be xm km. So it's actually just, I'm going to first just write all of Cm, n minus 1 minus km. And then I'm going to add on the set that's xm, n minus 1 minus km, union the element n. So what am I trying to do? I'm trying to cover the power set of 1 up to n. If I just take the chains, the symmetric chains I've got, that'll cover the power set of 1 up to n minus 1. So the sets I'm missing are the ones that contain n. So this is one way of covering such a set. Now I think I'm going to actually stop here because, right, so where were we? I was trying to prove that by the way, everyone can hear me, right? Right? Okay. I was trying to prove that the power set of the numbers 1 up to n has a symmetric chain decomposition. Right, so we were doing this by induction. The case n equals 1 was easy. Then we're considering n at least 2 and using the inductive hypothesis. Right, so by induction we got some symmetric chain decomposition C1 up to C capital N of the power set of 1 up to n minus 1. And we're trying to convert this into a symmetric chain decomposition of the power set of 1 up to n. Okay, so what we do is we just, so for each m, so I kind of introduce some notation up here where I let km be the size of the smallest element in Cm. And then I was able to write, because, so this requires, understanding this really kind of requires remembering this definition of symmetric chains. But by the fact that Cm is a symmetric chain, I can write it in the form, you know, a set of size km, which is the smallest size, a set of size km plus 1, km plus 2, all the way up to n minus 1 minus km, where, yeah, so that's just all this notation is. Right, so what we do is we take Cm and we define two different chains based on Cm. So the first one is you take, basically you just take the chain Cm, which is, you know, this stuff here. So it's, you know, this is literally the definition, or the, yeah, this is literally Cm. And then I add on one more element, which is obtained by taking the biggest set in Cm and adding the element n to it. Right? So this is one extra element. If you think about it, it's not hard to see that this is a symmetric chain in the power set of 1 up to n. Right? If you just check the definitions, of course, this new set contains the previous one, and it, therefore it contains all of the ones that came before it. So we're okay for that. The other one, so we also define a chain Cm prime, where instead of, so here I took the biggest element and I added n to it. What I need to do is I need to represent every set that has the number n in it, right? Because I haven't, yeah, those are the sets that aren't covered by the chains we had from the previous level, like for the power set of 1 up to n minus 1. So what I'm going to do in the second chain is actually kind of fairly natural. So I'm going to take all the ones I didn't add m to in the previous one, and I'm going to add m to it, or n to it. So, and all the way up to, so I have to stop at, so I'm not going to add n to that one because that one's already represented in the previous thing. So it's going to be n minus 2 minus km union n. Yep. Yeah. Okay. Oh yeah. I didn't write the second element above. I just wrote the dot dot dot. Yeah. No problem. Okay, so we just add n to all of the other things that we didn't add n to. And then again, it's not hard to check that this is a symmetric chain. So you just have to check it's a chain and that the sets have the right sorts of sizes. Actually, I'm not going to go into more detail on that because one of the assignment questions, if you've seen the assignment, is to basically just go into this proof and just check that this is these are symmetric chains, and that actually when you do these operations, it gives you a symmetric chain decomposition of the power set of 1 up to n. Okay, it's all very elementary. It's just really thinking about the definitions and stuff, and thinking how the induction worked. Yeah, I think it'll help you. I think the definition of a symmetric chain is kind of complicated, or it's kind of weird. So it's good if you get some hands-on experience using them. So I won't actually prove that this is a symmetric chain decomposition. But yeah, so the last things to verify is that well, basically that it is one. So these are, you want to show that these chains are disjoint. There's no common elements, and that they cover the entirety of the power set. And of course that they're symmetric chains, but that's not too difficult. Okay, so this is, like I said, that's on the assignment. Okay, we haven't proved Sperner's theorem, right? I stated Sperner's theorem, then we went into this lemma, and we haven't come back to it yet. So let's come back to it. So remember, Sperner's theorem says that the biggest antichain in the power set of 1 up to n has size n choose n over 2, where whenever I say n over 2, I mean the floor. Okay, so, right, so how do we prove it? So we use the lemma. So we find a symmetric chain decomposition of the power set of 1 up to n. Here's a thing. So remember what a symmetric chain is. It starts at so the smallest set has size k, where k is at most n over 2. And it goes up, the sets go up in size by 1 until they reach n minus k. That means that no matter what, they must have at some point included a set of size n over 2. Because if you start below n over 2 and you end above n over 2, or even if you start at equaling n over 2, you must contain something of size n over 2. So each chain does contain a set of that size. Okay. And actually, each chain must contain exactly one set of that size, because it couldn't contain 2 of them, because then it couldn't be a chain. Right, so basically because, there's lots of different ways to think about, but because the collection of sets of size n over 2 is an antichain, in each of these chains must contain a unique such element. So how big is capital N? Remember, capital N is the number of chains. If you think about it, every set of size n over 2 is in a chain. Every chain contains exactly one such element. So actually the number of chains is just n choose n over 2. Okay. No matter how the symmetric chain decomposition was constructed, it could be constructed the way we did it, or it could have come somehow from nature. Somebody magically appeared. No matter how it was constructed, it always has the same number of elements, same number of chains. Okay, so last line of the proof. Let A be an antichain. We want to show it's small. So what I can do is I can write the size of A. Since the CIs are partitioning, I can break up the antichain A in terms of which chains the elements are in. Right, so the size of A is literally equal to this value, because that's because it's important here that the CIs are partitioning of the whole power set. Okay, but remember, if I have an antichain in a chain, they can only contain one common element at most. So actually, each of these sum n's is at most 1. Okay, and of course, if I add up 1 n times, I get n, which is n choose n over 2. So that's exactly the inequality we were looking for. Right, so we get the bound that we were hoping to get. Are there any questions about that? Okay. So, what else did I want to say? Oh, this is just a fun thing. So, so we determined the size of the biggest antichain. A very interesting problem is to understand how many antichains are there. Right, that's a very, it's also a very challenging problem. And this is one of the, I think this is something something related to this is on the bonus problems.